This is the first solid-state battery in the world, the holy grail of battery tech. And I just met with Donut Lab, who say they've done what no one else could. Donut's battery could last 20 million miles in an EV. There's essentially zero risk of fire, charges to full in minutes, and the Lucid Air with 512 miles of range with a donut pack goes 730 miles with no change in weight. Clearly, this is a breakthrough moment that we've all been waiting for. But is everything as it seems? No one else has done it. So why would a small company from Estonia operating in stealth mode for the last decade be the first? I met with the team and had a chat with their CTO to find out. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by EcoFlow. This is one of the most exciting videos I've ever made. Without being too hyperbolic, this would be like going to a medical conference and seeing a booth from a company you've never heard of claiming that they've cured cancer. The biggest joke in the industry is that solid-state batteries have been 5 years away for the past 15 years or so. So with great claims must come great skepticism and excitement. In this video, I'll try to balance both. We've done as much research as we could, but the data is limited. So be sure to subscribe for future videos because this will be an ongoing research project. Donut Lab has been around for nearly a decade and started with an in-wheel motor. So Donut Motors, an operating system platform for integrating all EV components called Donut OS, and now Donut batteries. But in this video, we'll be focusing purely on Donut's batteries. We're going to include chapters so you can skip ahead to what matters to you, and I'm going to get into everything, but let's start with their claims. Donut Lab is presenting an all-solid-state battery for production vehicles, not a hybrid, not a semi-solid state, pure all-solid state. Ultra-high energy density of 400 watt-hours per kilogram, ultra-fast charging speeds. A charge speed of 1C means the battery could discharge 100% of its energy in 1 hour. Donut claims their batteries can do 12C, which is crazy. Full discharge or charge in 5 minutes. Almost unlimited cycles at 100,000 regardless of charge-discharge profiles. It's also extremely safe. No risk of fire or explosions when damaged. No risk of thermal runaway, no dendrite formation. It's non-combustible and non-flammable. It's puncture-resistant, non-toxic, and there's no environmental impact from supply chain or materials. The battery retains 99% capacity at negative 30 degrees Celsius as well as 100 degrees Celsius. Typically, when things get really cold, most EV batteries have to run heaters to keep the battery temperatures higher. But the Donut battery would deliver consistent power in that entire operating range. Now that's amazing, but what about price? Donut claims their solid-state batteries will have price parity with current lithium-ion batteries from day one, with future innovations bringing prices down even further. Nickel, cobalt, and lithium are expensive and are a limiting factor of bringing down battery prices. But get this, Donut claims their batteries have none of those materials, not even lithium. Managing resources intelligently is more important than ever. It's why I'm so excited about our sponsor EcoFlow and their Ecosystem Alliance announcement. EcoFlow is partnering with over 15 leading smart home brands like Homey by LG, GoE, Bosch, Shelly, and Google to build a connected home energy ecosystem. Your phone's components were made to work together. It's why they work so well. But your home is different. You might have a washer dryer from company A, a furnace from company B, and a car charger from company C, all with their own tech that can't talk to each other. With Ecosystem Alliance, each partner integrates directly with EcoFlow's system, enabling a single, all-in-one experience for users. The Alliance will prioritize broad compatibility using industry-recognized protocols when possible. So when your home acts more like a single connected machine, great energy resource management is possible. Appliances can understand energy use, energy costs, and make changes to help you save money. So learn more about how EcoFlow is bringing home tech together with the Ecosystem Alliance using our links in the description. Huge thanks to EcoFlow and you. Now back to the show. In engineering, everything is about optimizing trade-offs. Want something strong? How about lightweight? How about low cost? You can have two, but not all three. In the battery world, here's how this plays out. For stationary storage, weight doesn't matter, so we use lithium iron phosphate, which is less energy dense, but cheaper and longer lasting. Cars use nickel manganese cobalt, which doesn't last as long and is more expensive, but it has better energy density for longer range. Donut Lab solid-state batteries would be better in every way. Same price, way more life, way safer, and way more energy density. If you're thinking this sounds too good to be true, yeah. At the most basic level, every rechargeable battery has three core components: an anode, a cathode, and an electrolyte. The anode and cathode are the two electrodes where energy is stored and released through reversible electrochemical reactions. During discharge, lithium atoms at the anode give up electrons and become lithium ions. The electrons travel through the external circuit doing useful work, running a motor or a light. The lithium ions move internally through the electrolyte toward the cathode, where they recombine with the electrons and are stored in a lower energy chemical state. Charging simply reverses the process. In today's lithium-ion batteries, the anode is typically graphite with some small percent of silicon, which stores the lithiums between the atomic layers. The cathode is a lithium metal oxide like NMC or LFP, like we mentioned before, optimized for stability, voltage, and cycle life. The electrolyte is the unsung hero. Its job is pretty simple: conduct ions but block electrons. Modern batteries use a liquid organic electrolyte soaked in a porous separator. Liquids are excellent because they wet electrode surfaces perfectly and fill in microscopic pores and cracks. And they maintain low interfacial resistance even as electrodes expand and contract during cycling. Remember, in a battery, as they charge and discharge, temperatures can go up and down. You have thermal expansion and vibrations in the case of an EV. This has to handle all of that. This desk might seem smooth to you, but if you look at this zoomed up, you can get a sense of just how imperfect the surface is. Every one of those is a ridge. And this is why liquids make so much sense. One of the biggest limiting factors in battery performance and lifetime is the formation of lithium dendrites, microscopic needle-like metal structures that grow during charging. When lithium ions plate unevenly onto the anode, especially at high charge rates, these dendrites can extend across the electrolyte toward the cathode. In liquid electrolyte cells, dendrites can eventually pierce the separator, creating an internal short circuit, rapid heating, and in worst cases, have thermal runaway. To prevent this, modern batteries deliberately limit charging current, operate within narrow temperature windows, and avoid full lithium metal anodes altogether. A solid-state battery replaces the liquid electrolyte with a solid ionic conductor, ceramics, sulfides, or polymers. In theory, this enables higher energy density, non-flammable cells, and lithium metal anodes. In practice, though, it introduces brutal engineering challenges. One is interface resistance. Solids don't flow. Any microscopic gap between electrode and electrolyte becomes a high resistance barrier that kills performance. 2, mechanical stress. Electrodes expand and contract during cycling. A rigid electrolyte can crack, delaminate, and lose contact irreversibly. 3, dendrites do still exist. Even in solids, lithium can form needle-like dendrites that penetrate the electrolyte and short the cell. 4, manufacturing precision. Solid-state cells require near-perfect interfaces, ultra-flat surfaces, and often high pressure, none of which scale easily or cheaply. So how about use cases? Well, if it's cheaper, higher energy density, and safer, the donut battery would pretty much make sense in every single application. Motorcycles? Yeah, in fact, the Verge motorcycle will be the first, and it comes out in a couple of months, to feature this battery. EVs? Absolutely. Drones? Yes, it has higher energy density, which means longer range in ultra lightweight applications like drones. Robotics? Absolutely. How about grid energy storage? Well, we're seeing the rise of sodium-ion batteries, and if those were significantly cheaper than donut solid-state batteries, then some companies might still go that route. But if price is no option, yes, their battery would make sense there too. But one of the most amazing parts about this story is that it requires no rare earth materials. There's no geopolitical strife, and these materials can be sourced and built anywhere in the world. It's one thing to have a breakthrough of this caliber, but then it's another world entirely to manufacture them. So I chatted with Ville, their CTO, about this, and he mentioned that they have no plans of licensing this technology, and they plan on manufacturing the batteries themselves. They're producing pouch cells. Each cell is rated for about 125 watt hours of energy storage, and the module is rated for around 5 kilowatt hours, which means that each module contains 40 cells. They're available for large-scale production, according to them, today, not 2 years from now or something else. They say that they're ready today. If their claims are true, this is like the holy grail of battery technology. There's not a single trade-off, better in every way. Now, one thing I want to make really clear is that I wasn't able to get a lot of information from them in their interviews, and they told me from the very beginning that we're not going to talk about chemistry or manufacturing. Pretty much every question you and I probably have. But that in and of itself doesn't mean that they're lying or something. Here's why. Imagine if you had a winning lottery ticket, right? You're at a bar with all your friends, with hundreds of people, and the news comes on and reads the numbers, and you have the winning ticket. What do? Jump up and down and let everyone know that you have the winning ticket? Probably not, because maybe you get mugged and robbed, right? Maybe you keep it to yourself. There's a couple of things here. I asked about validation testing, third-party validation, and those are underway. They have to, because if they're going to sell this to vendors like Toyota, for example, or whoever, I'm just making that up, they will require this testing. And a redacted, publicly available version of some of that testing will emerge in the coming months. 2, if they have patents filed, when those patents hit, everyone will know how this is done. Okay. And 3, the Virgin motorcycle. When that Virgin motorcycle goes on sale, every company will buy one to tear it down to see how these cells are built. So this story is going to get out very quickly. And I think they're just trying to protect their IP for as long as they can. Okay. Now let's dig into some of the details. For example, the one little bit of proof that they provide is this video that they show their cells charging. In this video, on the left, you'll see a thermocouple. It tells you the temperature of the cell. Then there's the cell, which appears to be sitting on a black plate. I'm not sure if that's providing cooling or not. There's a kind of a wire running to it. Can't really tell from there. And then there's the machine on the right, the power supply that's providing the current and voltage. 4 volts is what it says up there. I think they're providing 4.2 at 270 amps. The first thought I had is if you look at the wires going into the negative and positive terminals, those wires aren't particularly thick. But think about this. To run 270 amps, you'd need like 4/0 cable, which is like this thick. Really, really thick cable. At least to maintain 270 for long periods of time. Those wires are clearly not that. But if they're just doing a quick test for 5 minutes, they could probably tolerate those wires getting hot for a while. Here's the next point. If you look down here, it has a M on it. And the reason why is the power supply they're using is the Delta Electronica SM500. It's a bidirectional power supply, and it can output 90 amps of current. So to be able to get to 270 for that one little pouch, they actually had to use 3 of these. And that M designates that that is the master. So that means that there's 2 others below that they're not showing, but they had to use 3 like industrial power supplies to be able to max out this battery. And they had to charge it 270 amps because by limiting the voltage to 4.2, the only other option was to increase the amperage, and that's what they did here. The system is running at a constant voltage of 4.2 volts. However, the actual voltage gradually increases from 3.9 to 4.2 as the pack charges up. That's to be expected. Temperatures only increase from 25 Celsius to approximately 63.3 degrees Celsius after charging from 0 to 82% in 4 minutes and 49 seconds, despite charging at over 10 C. Like I mentioned, there's questions that you're going to have and I'm going to have, and maybe one day we'll meet them on site and answer these, but is there thermal management involved? Is that black plate that the cell is sitting on a cooling tray? We don't know. At 63 degrees Celsius, it's well within the operational range of their claimed pack. Finally, let's just touch on one other detail, which is based on the data that we have here, this little pouch has a power density of 3.6 kilowatts per kilogram, which is pretty amazing, right? You would need a Tesla Model Y pack that weighs 1,000 pounds to be able to put out 250 kilowatts. This could do it at a fraction of the size. I just drove back from CES, drove all night to be able to make this video in time, and I'll still beat to the punch by my very good friend Ryan, who runs the YouTube channel ZIROTH. First of all, if you haven't subscribed to his channel and you like my content, go over there and subscribe. You'll love his stuff. But he pointed out that charging a cell at 4.2 volts could signal a lithium-ion chemistry because the charging voltage in all lithium-ion batteries is capped around 4.2 volts to avoid overcharging, which damages the cell and degrades the electrolyte like we mentioned. But I asked the team about this, and they made it very clear that the 4.2 volts they held the charge voltage to is to show you that they could be a drop-in replacement for any battery on the market today. That's the only reason. And they mentioned that there is actually a broad range of voltages that their batteries could accept. This led Ryan to conclude that potentially this could be like a supercapacitor or some sort of a hybrid battery. But supercapacitors also have major trade-offs. They struggle to reach high energy densities, above the tens of watt hours per kilogram, an order of magnitude lower than what Donut Lab is claiming. We actually did a video with skeleton supercapacitors in Estonia, actually next door neighbors of Donut Lab. Links to that video down below, who probably make the best supercapacitors on Earth. And they're in the 30 to 60 watt hours per kilogram range, which is nowhere near energy dense enough to be a battery replacement. So then naturally there's a few other possible theories. One is that this voltage thing that they could just have any voltage is probably an exaggeration, but there's a broader range than normal batteries. That could make sense for solid-state batteries because the decomposition of the liquid electrolyte is the main reason why you can't exceed 4.2 volts. But there is one other theory that I've been playing with, and that's the idea of a pseudo-capacitor. I found that in May 2025, a breakthrough from the Korea Institute of Science and Technology using carbon nanotube and polyaniline composite fibers reached 418 watt-hours per kilogram. And check out the rest of the specs. Volumetric energy density of 820 milliwatt-hours per centimeter cubed, power density of 1,150 watts per centimeter cubed, or 587 kilowatts per kilogram. Now, this is 163 times higher than Donut's experimental cell. It could be that they weren't really running the cells at maximum power for the experiment, or again, it could not be this type of battery as well. But cycle lives of over 100,000 charge-discharge cycles, exactly what Donut claims. Contrary to most solid-state batteries which have a ceramic electrolyte, this one is totally flexible. It can withstand over 10,000 mechanical deformations with no loss in performance, so you can twist and bend them into any shape. Since the polyaniline chains are anchored to the carbon nanotubes, the device can stay stable in high voltage settings without the typical polymer chain degradation that usually limits the voltage window of organic polymers. Sound familiar? It's also carbon-based, so non-toxic, readily available, and cheap. And the fact that it's based on carbon nanotubes is a strong indicator that we could be onto something, because that's exactly what Donut's main battery manufacturing partner, Nordic Nano, specializes in. Also, if it is a pseudo-capacitor, it even justifies Donut Lab calling the technology a solid-state battery. Pseudo-capacitance means storing energy via fast, reversible redox reactions on an electrode's surface. It replaces accumulating electrons on a surface in a capacitor, with bonding atoms on a surface through a chemical reaction, taking advantage of its higher energy density. It's literally like building a stack of millions of nano-sized battery cells, cathode, anode, conductor, and all, instead of making a large bulky anode with a large bulky cathode separated by a large bulky electrolyte. Call it a pseudo-capacitor or a pseudo-battery, but in the end, it actually is both. At this point, I should probably just take a quick minute and ask, what do you think? I'm sure at this point you've seen other people. We're not the first to make this video, and I'd love to know what you think. What are some of your theories? Have you found any other research that we've missed? Sound off in the comments below. But one of the most shocking claims of all is that this battery isn't just ready for production. It's already available for consumers in production electric vehicles, the first of which will be the Verge TS Pro motorcycle. This TS Pro claims more performance and real-world range than any electric motorcycle in the world. An older model had already set the Guinness World Record for the longest journey on an e-bike. The new 2026 Verge TS Pro model is now powered by the Donut Lab solid-state battery, making it the world's first production electric vehicle powered by a solid-state battery, and is set to crush that record. And you can buy one today for $29,900. Why is it so expensive? Well, it does have a new battery in it. Could they not have met that price parity target just yet? Or is it just a very low volume, bespoke type of product to begin with? We'll have to wait and see. But like I mentioned, as soon as this motorcycle hits the show floor, every question about this battery will be revealed, because you can guarantee every company on earth will buy one to tear it down. It's the hardest thing about engineering, is you want to be secretive, but the minute you sell your product, everybody could just rip it apart and find out about it. You ever had that experience where you do something, like let's say you're writing a paper, or you're doing some sort of like writing code or something, and then you lose it all. Like the power goes out, you lose your file, and you think, there goes 30 hours down the drain. Well, not really. Odds are the second time around, you can probably do it in like an hour and a half, right? That's kind of what happens here with batteries. All these millions of hours of research and billions of dollars is trying to find the perfect solid-state electrolyte or the right approach. But what if they found some alternative way to do something? And it's not that others can't do it. It's just that they thought of it first. Those are the easiest things to replicate and why they're going to be secretive. And I completely understand that. That to me isn't a red flag at all. I would operate the same way. And Donut isn't just going to be a battery research and development company. They want to manufacture everything. They've partnered with Watt Electric to develop a lightweight skateboard EV platform.
Hi, everyone. My name's Al. I work for Watt Electric Vehicle Company. We design, engineer, and manufacture lightweight electric vehicle structures and platforms. So we have two key technologies, what we call FlexTech, which is our patent-protected lightweight interlocking aluminium extrusion system. And we also have a laminated battery base plate, which is layers of aluminium and composite material bonded together. We take battery modules, build them onto the base plate, and then integrate them into the chassis of our vehicle.
So this is module to chassis, and this would be the donut
Yeah,
solid-state battery, right?
Yeah, so if we were, so it's possible to package 60 kilowatts of Donut Labs solid-state battery in this configuration.
From where to where?
Yeah, so kind of basically in the floor area. So we build it onto the laminated battery base plate, stuff the battery up into the vehicle, and it becomes integrated with the primary structure of the vehicle.
Now for the juicier part of this thing is the Nordic Nano Group partnership. Nordic Nano Group is a Finnish renewable energy startup founded in January 2024. Their process uses industrial scale screen printing to layer nanomaterials. And this is reportedly easy to scale and faster to set up than a standard lithium-ion battery line. Everything points to Nordic Nano being Donut's strategic manufacturing partner. Why? Well, Donut Lab invested in Nordic Nano Group since its seed funding rounds in early 2024. Donut Lab says its manufacturing facility is in Finland, where Nordic Nano is based, and where Nordic Nano has been building a large manufacturing facility since October 2024. Nordic Nano Group is opening a factory in Imatra, which will produce completely non-toxic and technically superior solid electrode battery cells.
Yeah, so I'm Ville Pipo, co-founder and chief technology officer at Donut Lab.
So tell us a little bit about the history of Donut and how we got here.
Yeah, so the whole history of Donut Lab is like 8 years. So we used to be on the same group with the motorcycle business and some defense side of it. Yeah, we started last year with the motors, so you see the motor family over there.
Yeah.
Those are all in-wheel motors. Of course, you can use them in many different applications like winches and elevators, and you see on the videos there's a whole bunch of like construction equipment and these kind of things. Then we do batteries, so we used to do like a whole bunch of different battery designs, but now we just like 4 days ago we unveiled the solid state battery. That's kind of the actual battery.
I've heard it's important. I
Yeah.
Solid state batteries, yes, that's why we're here.
Then we also do control units for the motors, and of course like the BMS system for batteries.
So the full stack of all the like the architecture
and also the unifying software layer. So on the corner there you should also do a feature on that, because it's basically how to remove all of the blockers for companies who are trying to build EVs and how to get to market.
So how big is the company?
We're a big fan of very small teams. So we're only like, I don't remember exactly, like 60, 70 people. So we've been doing this with a very, very tight-knit group of engineers. So for example, the team that's done all of the motors, that's only like just more than 10 people participating in all of that. And we've been developing these kind of vehicles and like applications for solutions for all kinds of customers with just some tens of people at the company.
Let's talk about the battery. I think that's the reason why I think this has become kind of maybe the most influential or important booth at CES, which is not an easy thing to claim, but I think you might have done it. There's several components to this. Obviously, the solid electrolyte, which is, I'd imagine, unbelievably proprietary. But then there's anode, there's cathode. What can you tell us? Just any details that are available for...
I can start with the stuff I'm not going to be talking about.
Sure.
So chemistry is quite different to what you've seen before with solid state lithium-ion based stuff. Another one is manufacturing method. We don't really describe it in any way. And the third one is like all of the suppliers and partners and all other like trade secrets that we obviously aren't telling about our motors either. So we're not going to go like publish all of the trade secrets. So what I can talk about is all of the specs and characteristics that you see on the stand here. So it's quite like easy to integrate with the kind of first go-to-market option. So we chose to do this kind of a pouch cell design exactly because this is very easy to do as a kind of drop-in replacement to any existing like lithium-ion, especially if you already are using like a pouch cell pack. Then you can just drop this in there, and we can make that in different sizes as well. Like it doesn't need to be exactly this, and it can be these like opposing tabs or longer or thicker or wider or whatever.
But this is probably, I would imagine, the preferred form factor versus cylindrical or prismatic. This might be the way that
cylindrical is not really on the roadmap because there's no kind of, we don't see any benefit in going cylindrical because in traditional lithium-ion it kind of makes sense because you can pack in stuff and then have those cooling snakes and everything. But that's quite complex as opposed to just slap a bunch of these into a pack and call it a day. Like this is so easy to integrate that it's the fastest go-to-market option.
Right.
Then in the future things get more crazy than this. Like we can do some more exotic designs, some more like exotic system level designs, and we're kind of like we did with the motor stuff. We kind of went and started reimagining what even is a architecture for a motorcycle or a car or a elevator or even like a washing machine or something. Now we're doing the same with energy storage, where we're starting with quite conventional looking thing, but what's inside is scalable both like in manufacturing capacity, but also in the kind of design, how you can make the vehicle in like interesting ways.
So you mentioned traditional lithium systems. So is this not a lithium cathode?
We're not discussing that much the chemistry, but this is a non-lithium.
It's a non-lithium, okay. And so then you mentioned the drop-in replacement. Knowing then it's not limited to the, like for the nominal voltage for, let's say, a lithium pack is 4.2 volts. You're matching the maximum, right? So you're matching that not because you have to, but because it makes sense for being a one-to-one replacement. But you have greater flexibility in terms of voltage with a system like this.
Yeah, I mean that goes into the assumptions, but the nominal voltage on this one is pretty much exactly the like 3.6 as you would get in a lithium.
3.6 to 4, something like that. Okay.
But then like people have been quite like they are speculating a whole bunch of things.
Yeah.
Like some of it is completely untrue and some of it is kind of close by. So we're not going to go into like saying yes or no in the end of it. You're not going to. And we're kind of unwillingly saying yes or no to the other things as well.
Okay. Okay. In that case.
But we will be doing this like third-party stuff that, of course, we've been doing like third-party analysis or validations in recent years, but that's more for our own sanity checks because developing something that kind of, even to myself, feels too good to be true, then of course we need to give it to someone else, like show me I'm not insane kind of stuff. But then we're not publishing those, but we are now working on stuff that we can publish, so it's going to be a well-curated set of data.
Okay. And is there a timeline for some of those publications to be made public?
I don't want to promise anything, but we're working on it right now.
Okay.
Yeah.
Okay.
Yeah.
No, that's more than fair. Now, let's talk about, I think the people watching this video know why this is really important. But if we could touch on some of the unlocks that are available with a solid-state battery, non-liquid electrolyte. One of them probably is maybe just power density or charge rate.
Yep.
I believe I heard some of the engineers say this can charge at 11C. Is that right?
Yeah, so that's what gets you the sub 5-minute charging time, yeah.
Right. And does that charge and discharge 11C?
Yeah. So you can see it on the video somewhere. The cell is basically just laying on a table somewhere, so there's no like active cooling being.
I've seen the video.
Pump it.
Yeah.
I'm sure you've been analyzing.
I've seen that video. 1 to, I think it was 5C, you could do it passively without even having any sort of active cooling. Yeah. And then the 5 to 11 envelope, maybe you need liquid cooling or some sort of active system.
Yeah, because that then kind of depends on the back level design. So there's many different ways of doing it. Like you can do a very capable design, like you can go way like below 5 minutes if you need to, if you're just pumping like a whole lot liquid. Like if you have a drone where that docks into a charging station and needs to go back like in 1 minute or so.
Right.
Sure, you can do that, but then you're probably abusing the cell more than you should.
Right.
But then, for example, Verge Motorcycles is going to start production with that one, and it's going to go into customers already in a couple of months only. and that's done in a very kind of the most simple and lightest weight pack design. So they are getting like charge time in 10 minutes, which is already like it's way better than any motorcycle out there. Electric motorcycle.
Yeah.
It kind of gets to like it's almost too fast because you can't even enjoy a cup of coffee in that. So then they don't really need to go to the very extreme with this, because then if you go to the extreme, you might increase complexity or cost or something like that. But this is very scalable. Like in any automotive use case, you would get to this, you would normally have some liquid cooling capacity. Like in the module there, you would have some cold plate kind of transferring the heat outside or away from the cell.
Help us kind of maybe understand the advantages of a solid state architecture with energy density. So this pack you're saying is around 400 watt hours per kilogram.
Yeah, or this cell.
This cell. The best NMC chemistries for a traditional lithium pack, probably in the 280s, is that fair to say? Kind of rough ballpark?
Yeah, something like that.
Okay, so that's a pretty sizable improvement. Is this just the beginning? This is like phase one, and 5 years' time we'd be seeing even better densities, or is there other physical limitations? You're not going to say. I guess the question is, like,
my boring answer of I can't really talk about it, but we're not anywhere near the kind of theoretical limits of this tech. Of course, we're going to keep on improving it over time.
Okay. How about like cold weather performance? How are the battery characteristics in cold temperatures, high temperatures? Is there greater deltas compared to traditional?
At least it's very wide compared to any lithium-ion cell. So we've been testing it already in like minus 30 degrees Celsius all the way to 100 degrees Celsius. And it's very stable and it's retaining like 99% or more than 99% of the capacity in those temps. It handles those temps very easily. But to be honest, I don't even know the limits because we haven't gotten around to testing the very limits.
Sure.
Of course, there's some use cases where someone needs this in the North Pole or something, then we're
negative 30C takes care of in most use cases. Maybe somewhere in Siberia or northern Canada there might be.
There was minus 35 in Finland just
a
week ago. Yeah. Wow. Luckily, I'm here.
Yeah. Do you see bottlenecks or issues with supply chain, or does this scale well for the future as this goes into every car? Every car maker will buy this if you could make them fast enough, right? So when that day comes, do you foresee challenges?
Again, sort of goes into the area where you're probably not going to believe it anyway, but I'll say it anyway. So this is not reliant on any geographical location of any kind. So we can do this in any continent.
It's amazing.
And it's abundant, low-cost material. So I don't really see any bottlenecks there. But of course, when we go from 1 gigawatt hour annual run rate to hundreds of gigawatt hours annual run rate, it's a challenge.
It's always a challenge
for any chemistry.
Yes.
Yeah, I mean 1 gigawatt hour run rate this year. Then next year, really depending on what kind of projects we get into production, because we don't want to pump out cells if there's the kind of projects that we are working on are not there yet. So it really depends on kind of is the ramp starting that month or is it that month or that month. But next year, be around 10 gigawatt hours, even going into 20 gigawatt hours run rate.
Okay.
So I'm not saying we're going to be making 10 gigawatt hours of cells next year. It depends on where the kind of growth curve is going on.
Okay. Two more benefits of the solid state battery that I've particularly been interested in. I don't mind the charge speed. I think my car charges fast enough. I've never had a big issue with it. But the two benefits I've been waiting very keenly for, one is the ability to just charge to 100% without thinking about it. Right.
Yep.
In my car, I keep it around 70 to 80 most of the time.
Yep.
So with your cells, you can charge to 100% every day. Is there pretty much every day 100%? So that unlocks already more potential energy in your pack that you're not using in the interest of saving the life. That's not a problem. The second is just the sheer number of cycles. 100,000 cycles is
which is completely overkill for any EV application.
Your car will be in the scrapyard long before.
So the whole point is that you don't really need to talk about lifetime anymore. Whatever vehicle you have, it's going to disintegrate before the battery is dead. So it's basically in any EV application, it's as good as immortal battery.
Pretty much, right.
But also in grid storage, you need a whole lot more cycles than any EV application. So or charging products where you would have this kind of a buffer battery in a charging station. You would need a whole lot of cycles in those kind of applications. So 100,000 cycles is there for a reason, but you're not going to need it in your motorcycles or sports cars.
What is the foundational physics reason why we're able to achieve these two parameters? One, 100% charge rate. I imagine they're related, and two, 100,000 cycles, right? So in my mind, I'm thinking dendrite formation is always a fundamental challenge in battery manufacturing. It poses a lot of risks, and there's just challenges around it. And in my head, you know, I don't work on this every day for 8 years like you have, but in my head, a solid-state battery could potentially go a long way to solve problems like dendrite formation.
Yep.
Is that part of the breakthrough? Is that part of the advantage of a solid-state architecture?
Yeah, I mean, I can say, like, if dendrites were a problem, then there wouldn't be this 100,000 cycle lifetime. Like, it's pretty obvious.
I can't imagine that it would.
It's been quite fun, kind of watching people try to figure out what this is online. Like, there's like every EV enthusiast and alike is kind of trying to be like a citizen journalist, trying to figure it out. And that's all kind of fun, but then we don't really have that many reasons to kind of show the world everything at the moment. But we will be eventually. Like,
you'll have
the next few months.
Yeah.
Like, because we now just unveiled this like 4 days ago, and absolutely every single customer that we are working on with the motors and our control systems and the software side, they're of course now also asking for the battery.
Of course.
And then there's like 5 times more companies also asking for the battery. So now we are in the process of hand selecting the ones that we are working with this year and next year and the year after and all that, and kind of form that into a growth curve. So those are the companies that we need to actually prove this to. And we are doing those in certain ways, but that doesn't really include showing it to all of the world. So
right.
Basically, we want to sort of maintain a healthy head start for people figuring this out. So that's why we've been very deliberate in being quite secretive about it throughout the years. But then there will be some opportunities to show more. And of course, when the bike goes on sale in a couple of months, or to customer deliveries, then like there's going to be companies who are tearing it down and looking inside and all these kind of things. But there's also going to be a bunch of YouTubers wanting to then take it for a spin and go for a fast charging station, or like try to experience the benefits opposed to what the previous generation of the bike was and all these kind of things. So yeah, of course we are working on those kind of things as well. But what people have kind of failed to understand is that like we don't have the 10 years of trying to get this from the lab to production kind of background or baggage like behind us. So
right.
Like we were very deliberate in keeping this as secret as possible, and we've been very successful at that when we were or until we were ready to go into production with it already. And now we are at that point, and you're going to start seeing this like more and more.
So the plan is that you will be the manufacturer, or will you work
we're manufacturing these. Yep.
Yeah. And is there any world where you would license the technology to others?
I mean, so far we don't really see a reason, because we want to control it. It's much like the motors again. Like a lot of this stuff kind of rhymes with the motor roadmap. So we are making our own motors, and we are even doing these like micro factories next to our like big customers, where we are still operating the factory, even though it's like next door neighbor to.
And the entire supply is for the company, but you're still the owner and operator of the micro factory.
Yeah, because we want to keep on iterating on the manufacturing technologies and all that, because that's as important as the actual like motor design. And the same applies here. Like we don't really see any reason why we would be licensing this, because we can just scale this production ourselves and therefore control the manufacturing development of that in the meantime.
Yeah,
It's not going to be just like okay, here's the manufacturing line, then copy paste it 1,000 times. But there's going to be some development as we go.
I've always heard building a battery factory is one of the hardest things. Just the cleanliness of air quality, particulate matter. It's just such a difficult thing to build. You have the expertise and you have the background and knowledge to be able to take this to the scale that the demand is going to warrant. That's amazing. That actually is, there's the research and like university, the brilliant minds that come up with some of this stuff. Equally difficult sometimes is just actually being able to make something
and also
reliably. And not every company has both parts, and that's where some of these different business models come from. But you're saying you're going to do both.
Yeah, and also one like crucial aspect here is that now that we unveiled this, which is exactly what we expected, like everyone in the battery industry wants to work for us now. So of course we're going to be like.
Oh, you mean the people applying to work for you?
Yeah.
Oh, I hadn't thought of that.
This is always like we're going now into business, but the scaling up requires all of the best talent in the world, and now we are accepting quite a few of those people. We're still keeping the team very small, so like the same as we're doing with motors, it's just like 10 people doing all of it. But there are 10 of the best people in the industry doing all of it. We're keeping the battery team also very small, but we want the best people to join. It's kind of the point.
It's hard to like forecast cost, especially until you hit some kind of a scale, and the scale will determine the price and things. But if you looked ahead a few years into the future, do you see solid-state batteries being kind of a equivalent price point replacement for traditional tech that we have today? Will it be a premium segment product that'll go into maybe the next electric Porsches and like more higher-end applications? Where do you see the price falling? Just general terms.
Yeah, so this is one of the key differences between this technology and like other solid-state companies, because usually solid-state batteries start at like many times more expensive than lithium-ion, and then they have like a price down curve of some sort where they will meet the current lithium-ion price in like 29 or 31 or something like that. But this is already like price parity or lower already starting this year, and then when we are ramping up, then we can get to significantly lower. So that's why we are open to all markets. So it's not just high-end automotive or not just drones or like medical devices or like consumer electronics where you might pay a lot more per kilowatt hour. But this is also going into grid storage and these kind of things where the margins are lowest and the price is the lowest.
Wow. We've lived in a world where the last 10 years it's specific chemistry. Do you go NMC or NCA? Do you do lithium iron phosphate, sodium ion? You have all these decisions, like the engineering triangle of decisions to try to optimize for cost. If it's a stationary solution, you don't need to have the highest the energy density. You can get a cheaper battery, and it'll last longer. There's all these trade-offs and pros and cons. This sounds like it's just the obvious choice in almost every application.
If someone is making a shipping container sized like a lithium iron phosphate battery, and we can fill like 3 times the capacity in one container, then you need a third of that whole like battery park as a footprint.
Right.
So of course it then makes even more sense in like the whole system level stuff. And the same applies to like automotive or any other application. Like if we can make the whole system smaller, then usually it's also lower cost. But already at the cell level, without even talking about the system level, we are at price parity or lower.
How about the safety component? I did see some videos, some of the torture testing that you put the batteries through. We know the liquid electrolyte it's the part of the battery that really is problematic, and you're getting rid of it. So I'd imagine just by design, it's an inherently much safer battery.
It's much safer than lithium-ion because of exactly the reasons you described, where we don't have the liquid electrolytes, which is kind of the scary thing there, and the dendrite formations and things being like thermal runaway-ish.
Yeah.
This is much safer, which is why like aerospace industry, like things that fly and have humans on board, they kind of need this but even like things like electric bikes where you're charging in your apartment or something. I mean, a lot of like those lithium packs catch fire in your garage or something because they are usually the lowest grade lithium as well.
Right.
But now, if we can do it in a safe way and we can actually double or triple the performance of that pack, then there's applications as well.
Yeah.
So safety is much better than lithium-ion, which is usually the case for solid state. Like no matter what kind of chemistry you're using, it's usually the case that the solid state stuff is kind of safety first.
But what do you think? I'd love to know what you found or researched or where you fall on this. Sound off in the comments below. And until future news breaks, we will cover more stuff in future videos. Check out some of our other videos. Like I've mentioned, we've covered all this stuff exhaustively. We've covered solid-state batteries, supercapacitors with skeleton, and everything else. We're proud to put links there down below. I'm Ricky with Vinci. Thank you so much for watching.